Contributions include research on scaling laws in machine learning, GPT-3, Codex, and more recently, AI safety work, such as RLHF for helpful and harmless language assistance and constitutional AI. Welcome to the stage, Jared Kaplan.
Thank you so much. It's really fun to be here. So to shorten all of that up, I'm the leader of the team at Anthropic that built our AI assistant Claude that hopefully you may have seen, may have played with, and hopefully many more people will be playing with soon. So I'll be talking a little bit about the trends that we see driving AI progress and why we expect it to continue and to get even more exciting, maybe a little bit scary. So there are sort of two things that you need to continue to make progress in AI systems. There is an exponential trend in using more compute power to make AI systems better. And there's a similar trend in algorithmic progress. We're making these systems more and more efficient. And that's really driving what you see that's possible this year that wasn't possible a couple of years ago, and why I think the sort of future is very interesting. The other thing that you need for these systems, for these generative AI systems, is that you don't want them to just spew garbage. You don't want them to hallucinate. So you need some kind of steerability or reliability or safety work to ensure that these systems behave well. And so Anthropic really aims to keep building some of the most powerful frontier AI systems in the world while focusing a lot of our research effort, really maybe the majority, on making these systems more steerable, reliable, and safe. And we really think that AI, as probably most people believe since you're here, is going to permeate the economy and grow in importance over the next few years. So who are we? And maybe I'll actually give you a slightly longer history lesson since we're at the Computer History Museum. So the folks at Anthropic, including Dario, our CEO, were in some sense the team that built GPT-3. And you can see the original GPT-3 paper. Dario was the director of the project. The lead engineers now run engineering at Anthropic. But it's sort of interesting to ask, since we're here, where did these systems actually come from? This is GPT-3. What about GPT-1 and GPT-2? And so I think the interesting person who is on this paper but not highlighted as much is Alec Radford, who, still at OpenAI, built the original GPT-1 model. What then happened was that Dario had the intuition from seeing a lot of AI systems that had been trained that scaling the system up further would be very interesting. And so that conviction, which didn't bear fruit immediately, led to GPT-2. GPT-2 is an interesting system, but it seems like it was on track to be amazing from where we stand now. But actually, when GPT-2 was released, Google released a paper, I think within a year, calling it sort of antiquated, defunct technology. They said that these language models weren't really going anywhere. They had better things. And Dario really had the conviction that was bolstered by the research that many of us did that exposed these exponential trends, that this was, even if GPT-1 wasn't commercially valuable, even if GPT-2 was impressive but not ready yet, that we were on some trend scaling towards much more useful, powerful systems. And so this is sort of the real world evidence for these trends. So if you look at the amount of computation that was being used and still is being used in the AI field, it's really, really growing exponentially. And an interesting thing that I observe, I mean, I'm not a chemist by any, but I took chemistry in high school. And you might remember there's this number called Avogadro's number that's an immense number. It's like 6 times 10 to the 23. It's like a billion, billion, billion. And I always thought, well, chemistry is really weird. We have this giant number. These numbers are not useful in any other place. And now we're at a point after sort of 70 years of computer science where we can train models with more than Avogadro's number of floating point operations. So these models like sort of GPT-3, GPT-4, et cetera, are trained using something like 10 to the 24 floating point operations. It's a tremendous, tremendous amount of computation that sort of human civilization is able to put together to train these systems, and this is the trend. But I think everyone in this audience probably knows that this is really expensive. Training these larger and larger systems costs more and more and more money, even with advances in computer chips. So why did Dario and why do we continue to have the conviction that this is where things are heading, even though these systems are so big, so expensive? And that comes from scaling laws, which were sort of a quite precise scientific discovery we made a few years ago. First with language models, literally with GPT-1 and GPT-2, and then we investigated generative AI across the spectrum of modes, multimodal systems, systems asked to solve math problems, systems asked to generate images, all the same way. There's this sort of grand unification that's occurred in AI where we can use the same kinds of systems with different kinds of data and get strong results regardless. And so what all of these rainbow plots show is that there's this increasing trend where models are becoming more and more capable. They're fitting their data better and better and better as you scale up the amount of compute data and model size that you use to train them. And so based on these scaling trends, which you can see on these plots range over sort of a factor of 1 billion in scale from tiny amounts of computation to vast amounts of computation, because of these scaling laws, we thought, we'll make a bet, we'll train a model for maybe order $10 million and see what it can do. And that's what led us to build GPT-3. And that's, I think, what's sort of powering generative AI these days. And so to sort of look at the explosion in AI capabilities on a different axis over time, there was sort of this early era of AI systems that were trained to do very specific restrictive tasks, like playing a single board game. And early researchers would try to train these systems to maybe generalize to other kinds of games. Can you play Space Invaders and also play Pong? But the results weren't very good. All of these systems were trained to just do sort of one specific thing, to classify images, et cetera. And then around 2018, 2019, we started to get these generative AI systems, the early language models, that are able to actually do more general types of tasks, GPT-1 and GPT-2. And then in the last couple of years, these systems have finally become sort of useful for something. At first, they were useful for, say, autocomplete for code. They weren't very good chatbots. And then very, very rapidly in the last couple of years, we've gone from systems that are not very smart and not very general to systems that can do as well as high school students on most academic subjects, maybe as well as college students. They can translate between languages. They can exhibit complex behaviors like adapting themselves to users in undesirable ways. We call this sycophancy. I'll talk in a bit about the fact that these systems can improve themselves by thinking out loud and by training themselves. These systems can play complex games involving deception. So this has really blossomed, and I think the key drivers here are scaling up compute, and also, as more and more researchers get excited about this field, there's been really rapid algorithmic progress that makes these systems more efficient and makes it even better as an investment to build state-of-the-art AI. And really, the algorithmic progress has been faster than even I expected. Now, that explains how these systems are becoming more general and more powerful. But why do we need safety work? Why do we need steerability, et cetera? And this is something that we've all encountered. Even when we try to make these systems sort of do what we want, things are moving so quickly that researchers make mistakes, and models that we deploy make mistakes. And I think these are sort of cherry-picked examples, but there are these problems where systems can be tricked into saying offensive things, or they hallucinate and don't give you reliable factual information. And when when we survey customers at Anthropic, the number one thing that people would like to see improve about these AI systems is to be more honest, to be more factually accurate, to not hallucinate, to be able to be trusted. And that's why we're so focused on these questions. And we are making rapid progress in this area. It's something Anthropic and many others are very focused on. But with the extreme speed of development of the technology, it's still hard to keep up. So this is sort of a timeline of some work from folks at Anthropic and others on controlling, steering, and better understanding these models. So early on, in ancient days in 2016, there was this paper by Dario and others on trying to make concrete the problem of how are we going to control AI systems. And then there was sort of this steady progress. Reinforcement learning from human preferences was first developed about 5 years ago. That's what's heavily used in Claude and ChatGPT. There was simultaneously progress in interpreting how these systems work, feature visualization, and understanding the neural circuits in neural networks that cause them to behave in one way versus another. There was these developments of scaling laws that I mentioned that explain why increasing investments are worthwhile and why they're probably going to continue. And more recently, we developed Claude and constitutional AI that I'll talk about in a minute. So what is constitutional AI? Well, this is a single slide about a complex subject. But to explain how constitutional AI works, I'll go back to how do we use human-in-the-loop or human preferences to control AI systems. So the basic way we do that is very simple. We have these generative AI models. You can sample from them, and they'll say anything. So you have these systems sample 2 possible responses to some query, and you have humans evaluate which response is better. And then we just train the systems to reinforce the behaviors that are desirable and avoid the behaviors that are undesirable. So it's simply, we have a pair of responses for models, and we go in the ratchet direction of good behavior. We disincentivize the bad behavior, and with tens, hundreds of thousands of human conversations, we can train AI systems to be better. So what is constitutional AI, and how does it differ from that process? With constitutional AI, we can make the principles AI systems follow transparent. We can share them with the world. We can iterate much, much more quickly because we don't need humans in the loop at all. And we can work to improve future AI systems at sort of a faster clip. So the idea of constitutional AI is really, really simple once you understand this idea of human-in-the-loop preference training. Instead of asking people, say crowd workers, what behavior from an AI do you prefer? We ask the AI itself, according to a list of principles, this constitution, what behavior would be better. And so we replace human-in-the-loop training, human feedback, with AI self-evaluation based on the constitutional principles. And so that allows the AI system to effectively train itself, which means that you can iterate, you can train a new AI with a new list of principles in a day rather than having to wait months to talk to crowd workers, tell them what to do, and collect more interaction. And furthermore, it works as well or better for steering AI systems away from harmful tendencies as human feedback. So this plot from one of our scientific papers, all it's really showing is that there's this Pareto improvement in how helpful and harmless, which means inoffensive, non-toxic, non-racist, et cetera, the model is. There's normally a trade-off where if you tell AI systems don't help people rob a bank, they become less helpful generally, and constitutional AI helps us to improve there. So that is how we train Claude. We train Claude with a mixture of constitutional AI and human feedback from domain experts in order to improve its utility say, for software engineers or lawyers or other potential customers, because of course experts know best what they actually want the AI system to do. So we blend those things together, and that's how we train Claude. And we're finding a number of use cases. We just started testing Claude with customers back in January and February. We've just launched, and we already have a lot of different use cases. So of course, Claude can be used for search, for content generation, for summarization, for productivity. It could be used as a coding assistant, can debug code. There are all these different use cases which just sort of are kind of the norm in generative AI. And in order to reach more customers and really quickly ensure privacy and safety of customer data, we're partnering with Amazon on Amazon Bedrock to deploy Claude at even greater scale. So I'll show you a couple of use cases and a couple of videos. So if you've used Notion, Notion has integrated AI. Notion was a very early mover in integrating AI onto their platform. And there's all sorts of different features that Claude is being used for within Notion to write, to summarize, et cetera. So this is just an example. And Notion's a really exciting partner for us because they iterate really, really quickly. Whenever people on my team are frustrated that Claude can't do something, I tell them, well, don't tell customers it can't do that, because in 2 months it will be able to do that. And Notion's moving really, really fast as well, and so it's really exciting to iterate with them to add more features, and I hope there will be more to come soon. Another example of maybe our earliest customer is Robin AI, who has a legal workflow to make lawyers much more productive. And this is obviously an area where there's a lot of value. Lawyers' time is valuable, and so if you can make them more productive, that's helpful. Actually, we've had pushback from lawyers that they don't want this technology anyway because they bill by the hour, and they're afraid. They literally ask us if it's only going to take us 10 minutes to write this contract, like what do we tell our customers, what's going to happen? But that's the problem for lawyers. So Robin AI uses Claude to basically instantaneously edit long contracts to make them more favorable to one party or the other. So if you've worked with lawyers, you know that there's a lot of details in legal language that you can change to make things safer for you in court. And this is sort of an example of Claude following Robin AI's instructions to make contracts that the party they're advocating for will prefer. Oh, good, we solved that problem. So this is a video. It's going by a little bit fast, so maybe we can do it twice. This is a video of a new feature that we just released, and I think many people are interested. So something you may know if you've been paying close attention to generative AI and generative AI language models is that language models have a context window. Unlike us, they don't remember forever. They only remember for some finite number of words that they've recently seen. And the earliest language models maybe only remembered a few hundred words. That was the limit. So that number has expanded over time. The early versions of Claude had about a 6,000 word or 9,000 token context. And we felt like many customers were viewing this as a problem. You'd like to be able to give Claude a whole book or a giant document or your financial report and have it answer questions or write a summary. And so we've, with our newest release of Claude, we've introduced, let's see. We've introduced a 100,000 token context window so that basically you can fit a document the size of The Great Gatsby entirely in Claude's context window. So what this video is showing is that Claude doesn't know anything about LangChain. Maybe most of you in the audience do. LangChain is this great platform for combining different language models together to do complex tasks. Claude doesn't know about LangChain, but if you give Claude the entirety of LangChain's documentation, Claude can then write and explain code to use LangChain with Claude. So you can give these entire manuals of how to use a new API and ask Claude to help. So the final video is just about speed. So one thing that we've tried to do in making Claude as useful as possible is reduce latency. No one really likes waiting for language models to generate samples word by word. And so this is just a comparison. I mean, there are a lot of language models out there. There are a lot of different performance characteristics. But Claude Instant samples about almost 500 characters a second. So that really, for a lot of use cases where latency is important, where you need to get an answer quickly, this is something that we've really optimized, and we hope it's useful for all of our customers. Great. That's it.